welcome. You're here because you want the real story on the cutting edge, right? The stuff that's actually shaping tomorrow.
Uh-huh.
And you want it fast, clear, without getting bogged down in, endless jargon, just the core ideas.
Exactly. And today, that means quantum information.
Yeah.
You've shared some really great material covering everything from the absolute basics up to the really big potential impacts.
Right. So our mission really is to pull out those key nuggets for you.
Right.
What is quantum information? What's its power? And importantly, what are the big hurdles?
Sounds good. So where do we start? The qubit, I suppose.
Yeah, let's start there. The qubit. It's the heart of it all, isn't it?
It really is. It's the quantum version of the classical bit, the 0 or 1 we all know. But, and this is the crucial bit, excuse the pun,
Oh, nice.
unlike a classical bit, a qubit can be 0 and 1 at the same time. That's superposition. Schumacher really helped popularize that idea back in '95.
Okay, so superposition. I sometimes think of it like a Dimmel switch instead of a simple on-off switch. Is that fair? A classical bit is just on or off.
That's actually a pretty good analogy, yeah. A qubit can be in that in-between state, a combination of 0 and 1.
And that's what gives quantum computers their edge, exploring all these possibilities at once.
Exactly that. It's called quantum parallelism. It allows for, well, a massive increase in processing efficiency for certain kinds of problems that classical computers just get stuck on.
Okay, so qubits have superposition, but then there's this other spooky thing, entanglement. What's the key takeaway there?
Entanglement. Yeah,
Mm.
it's one of the weirdest parts. Basically, you can link two or more qubits so their fates are intertwined no matter how far apart they are.
Intertwined how?
Well, if you measure the state of one, say, you find out it's a 0, you instantly know the state of the other one, even if it's miles away. David Deutsch was looking into this way back in 1985. It's fundamental for computation.
So, like our dimmer switches again, you adjust one, and the other one, way over there, instantly changes to match or oppose it somehow.
Sort of, yeah. That correlation is incredibly powerful. It means sometimes, like in Deutsch's problem, you can figure out something about a whole system with just one look, one query. Classically, you'd have to check it multiple times.
Wow. Okay. That sounds super efficient,
Ah.
but I get the feeling there's a catch. These qubits sound delicate.
Oh, extremely. That's the big challenge. They're incredibly sensitive to, well, everything. Noise from the environment, temperature changes, stray magnetic fields,
And that messes them up.
completely. It causes something called decoherence. The qubit basically loses its quantumness. That superposition and entanglement just collapses. It becomes like a boring old classical bit.
So keeping them quantum is the hard part.
It's a huge part of the research, yeah. Developing error correction codes, ways to protect the quantum information, and just finding better ways to control them. People are trying all sorts of things, like using photons or tiny superconducting circuits. Lots of different approaches.
Okay, so we have these powerful but fragile qubits. To actually do something with them, we need quantum algorithms, right?
Exactly. Quantum algorithms are the instruction sets designed specifically to run on these quantum computers to leverage superposition and entanglement.
And they're not just faster versions of normal algorithms.
For certain problems, they offer a fundamentally different and sometimes dramatically faster way of computing.
Let's talk examples. Shor's algorithm always comes up. Why is that one such a big deal?
Right. Shor's, Peter Shor, 1994. It's famous because it can factor large numbers incredibly efficiently in polynomial time.
And why does factoring large numbers matter so much to, us?
Because almost all of our current online security, think secure websites, encrypted emails, financial transactions, relies on the fact that factoring large numbers is extremely hard for classical computers. It would take them billions of years.
Uh-huh.
Shor's algorithm on a powerful enough quantum computer could potentially do it. Well, much, much faster. We're talking an exponential speed up.
Wait a minute. So this algorithm could basically break modern encryption, all the stuff we rely on?
Potentially, yes. If, and it's still a big if, someone builds a large enough, stable enough quantum computer. It's a serious concern for cybersecurity. It's why people are already working on quantum-resistant cryptography.
Okay, that definitely highlights the impact. Wow. What about other algorithms? Grover's.
Yeah, love Grover, 1996. Grover's algorithm tackles searching unsorted databases. Think finding a specific name in a massive, unordered phone book.
Okay.
Classically, you might have to check half the entries on average. Grover's can do it much faster in roughly the square root of the number of entries. So for n entries, it's order square root n versus order n classically.
So not exponential like Shor's, but still a nice boost, a quadratic speed up.
Exactly. It's a significant improvement for many tasks, especially in data analysis, maybe machine learning, anywhere you need efficient searching.
What other kinds of problems are these algorithms good for?
Well, one huge area is simulating nature itself.
Mm.
Quantum mechanics rules the world at the atomic level, so using a quantum computer to simulate molecules, chemical reactions, new materials. It's a very natural fit.
That makes sense. Using quantum to study quantum.
Right. There are algorithms like VQE, the variational quantum eigensolver, that are already being explored for this. These are problems classical computers really struggle with.
And beyond simulations.
Processing complex data. Think AI and machine learning. Quantum algorithms might offer new ways to handle things like support vector machines or clustering data. Also, optimization problems, finding the best solution out of many possibilities. That comes up a lot in finance, logistics.
So for AI, maybe getting past limitations where current algorithms get stuck in sort of okay, but not great solutions?
Potentially, yeah. Exploring a wider solution space. And sometimes they can represent complex data more compactly, needing less memory.
This sounds like a whole new way of thinking about programming, though. Is it hard to write these algorithms?
It definitely requires a different mindset. But tools are being developed. Languages like Q# from Microsoft or Qiskit from IBM, they provide higher-level ways to build these algorithms without needing to be, a quantum physicist for every line of code.
Okay, so we've got the qubits, the algorithms, but what about the actual computers? Quantum computing itself, it's not just software, right?
No, absolutely not. It's a whole new type of hardware. A completely different paradigm for processing information built on quantum mechanics. Superposition is key, letting it do many calculations sort of in parallel.
Harnessing the weirdness, basically.
Pretty much. Things like wave-particle duality, the fact that quantum stuff is inherently probabilistic, it all plays a role. You build qubits from physical systems, those photons or superconducting circuits we mentioned, and then you manipulate them using quantum gates.
Like logic gates in my laptop, but quantum.
Analogous, yes. But these gates use quantum effects like entanglement and interference, where quantum waves can add up or cancel out to perform operations.
And the potential impact. We mentioned drugs, materials.
Huge potential. Designing catalysts, optimizing financial models, cracking logistical nightmares, tasks that are just too complex for classical machines could become feasible. That's the promise.
But we're not there yet. Still early days.
Definitely still early days. Scalability is a massive challenge. Building machines with enough high-quality qubits. And robustness, making them resistant to that noise and decoherence. Error correction is absolutely vital. People are working on things like surface codes, topological codes, ways to build fault tolerance.
What does the hardware actually look like now? Are there working prototypes?
Oh, yes. Companies like IBM have their quantum experience platform. Google built processors like Bristlecone. They've shown they can run complex simulations, do some optimization tasks. It's impressive progress.
But still fragile.
Still quite error-prone, yes. Getting the error rates low enough for really complex algorithms, like Shor's on a big number, is still a major hurdle.
And that scalability ties back to the algorithms too, right? Making algorithms that work on these slightly noisy, medium-sized machines we have now.
Absolutely. There's a whole field of research around that. And yeah, the dream of running algorithms like Shor's is a huge motivator for building better hardware.
Okay, shifting gears slightly. We've talked about processing information. What about sending it securely? That's quantum communication.
Exactly. Using quantum mechanics not just for computation, but to make communication itself more secure, maybe more efficient. It relies on sending quantum states qubits, or using shared entanglement between the sender and receiver.
Sending actual qubits instead of just classical signals.
Right, and that opens up new possibilities. Because of superposition, a qubit can carry more information. And entanglement creates these incredibly strong links that are useful for security. The big advantage is detecting eavesdropping.
How does that work? Classically, someone can often listen in without you knowing.
It's fundamentally different in quantum. This brings us to QKD quantum key distribution. Now, usually QKD isn't about sending the secret message itself quantumly. It's about creating a shared secret key securely.
Ah, okay. So you use quantum mechanics to agree on a key, and then use that key for normal encryption.
Precisely. The most famous protocol is BB84 Bennett and Broussard, 1984. It often uses single photons and their polarization like the direction light waves wiggle.
Okay.
The sender sends photons, randomly choosing how they're polarized, using different bases like horizontal, vertical, or diagonal. The receiver measures them, also randomly choosing a basis for each photon.
So sometimes their choices match, sometimes they don't.
Exactly. Afterwards, they talk over a normal channel. This part doesn't have to be secure, and just compare which bases they used for which photon, not the measurement results themselves.
Okay.
They only keep the results where they happen to use the same basis. In theory, those results should be identical.
And if they're not identical?
That's the alarm bell. If an eavesdropper, let's call her Eve, tries to intercept and measure the photons, the act of measuring a quantum state inevitably disturbs it, especially if she guesses the wrong basis.
So trying to listen leaves fingerprints.
Exactly. Eve's measurements introduce errors that the sender and receiver, Alice and Bob traditionally, will detect when they compare a sample of their results from the matching basis measurements. If the error rate is too high, they know someone was listening, and they discard the key and start over.
And this is related to that no cloning thing?
Yes, the no cloning theorem is fundamental here. It says you can't make a perfect copy of an unknown quantum state. So Eve can't just copy the photon, measure the copy, and send the original on undisturbed. Any measurement risks changing the original.
That sounds way more secure than just hoping nobody's tapping the line. Are there other uses for quantum communication besides keys?
Definitely. That sensitivity of quantum states is great for sensing. Ultra-precise measurements of magnetic fields, gravity, time. Quantum sensing is a big related field. But yeah, QKD is the main communication application right now, with some early commercial systems being deployed, though scaling it up still has challenges.
Okay, so QKD is a big part of quantum cryptography. Is that basically the same thing?
QKD is the most mature application. But quantum cryptography is the broader idea of using quantum mechanics for security. It's all based on that principle. Measure something quantum, and you risk disturbing it, revealing your presence. Besides BB84, there's Eckert-91, which cleverly uses entanglement itself to generate the shared key.
So the security comes from physics, not just hard math problems.
That's the core idea. Classical crypto relies on problems believed to be hard for classical computers. QKD relies on the laws of quantum mechanics, like no cloning and the uncertainty principle. In theory, it offers security proof against any computational power, even future quantum computers trying to break the key exchange.
You mentioned using it for things like health records. Makes sense for really sensitive data. Have they tested this over long distances?
Yeah, there have been some impressive demos, over thousands of kilometers of optical fiber, even via satellite. But practical implementation isn't perfect.
Ah, the real world strikes again.
Always. Things like side-channel attacks, finding weaknesses not in the quantum theory, but in the actual hardware devices, like maybe tiny variations in timing or brightness give something away, or imperfections in the photon detectors. So there's ongoing work on countermeasures, like using decoy states or better hardware to plug these practical gaps.
So strong theory, but engineering challenges remain.
Exactly. And looking ahead, the threat of quantum computers breaking current crypto means we urgently need new classical algorithms that are resistant to quantum attacks. That's post-quantum cryptography, things like lattice-based or code-based systems. It's a whole separate but related race.
It feels like everything's heading towards connecting these devices, quantum networks.
That's the logical next step, yeah. Moving beyond just point-to-point QKD links towards a real network infrastructure that can transmit quantum information, share entanglement more widely. The goal is something much more secure and potentially more capable than classical networks.
So linking quantum computers, or enabling new kinds of secure communication.
Both, really. As of last year, people were already building and testing prototypes, focusing on secure communication for banking, healthcare, IT. QKD is the first thing running on these early networks.
But the bigger vision is the quantum internet. Is that real?
It's the ultimate goal for many. A network that allows quantum computers anywhere to communicate quantumly, to share entangled states. Imagine distributed quantum computing linking smaller processors together to tackle huge problems. Or truly secure cloud computing.
Sounds incredible. What's stopping us?
Well, all the challenges we've mentioned, building complex quantum hardware, dealing with errors, the sheer difficulty of transmitting fragile qubits over long distances without losing them or their quantum properties. And of course, thinking about new security threats, quantum hacking that might emerge.
Okay, we've covered a lot of theory and potential. What about now? What actual experiments are pushing the envelope today?
Oh, lots of cool stuff. For instance, people are experimenting with high-dimensional entanglement. Instead of just a qubit, 0 or 1, encoding more information onto a single photon using more complex states.
Why do that?
It could potentially boost communication capacity, like getting more data through the quantum channel. They've done proof-of-principle experiments showing it can work. using clever statistics to verify it.
More bandwidth for quantum comms.
Hmm.
Okay. What about computing experiments?
Finance is a hot area. Studies are showing quantum algorithms, even on relatively near-term processors, maybe 50, perhaps 300 qubits. Students could start matching or even beating classical methods for things like pricing derivatives. They've even developed quantum-enhanced machine learning for predicting credit risks.
Money talks, I guess. What about tackling that scalability problem we keep mentioning?
Yes, distributed quantum computing is getting real experimental traction. There was a great experiment, I think Oxford was involved, where they linked two separate small quantum processors using light, a photonic network, and used quantum teleportation to run logic gates between them.
Like building a bigger computer out of linked smaller ones, a quantum cluster.
Exactly. It's seen as a very promising path to scale up without having to build one single impossibly huge processor.
And the error problem. Are we actually running algorithms on error-corrected qubits yet?
We're getting there. There was a big collaboration, Harvard-led, I believe, that recently demonstrated running algorithms on a system with 48 logical qubits. Logical qubits are the error-corrected ones. They performed hundreds of complex operations. That's a huge milestone.
So progress on fixing the errors in real time?
It's a major step towards fault-tolerant quantum computing, yeah. But the overhead is still significant.
Overhead.
You need many physical qubits, maybe hundreds or thousands, just to create one stable logical qubit. Plus, connecting and controlling all those physical qubits gets incredibly complex as you scale up. High-fidelity gates, effective error correction, connectivity. These are still the big mountains to climb.
It's been a fascinating journey through this quantum world. As we wrap up, what are the big takeaways, the key future directions and challenges we should keep an eye on?
Well, the transformative potential across so many fields is undeniable. Healthcare, finance, materials. But integration is key. How will these quantum systems work alongside the classical computers we already have? They won't replace everything.
Right, finding the right balance. And presumably, the algorithms will keep getting better.
Absolutely. Expect more breakthroughs, especially maybe quantum-inspired classical algorithms, better machine learning, more sophisticated financial models. But making them accessible, usable, that's another challenge.
And doing it all responsibly.
That's becoming a much bigger focus, thankfully. Thinking about the societal impact, the ethics. We're seeing governments and funding agencies starting to build responsible innovation frameworks right into their quantum programs.
Right, and simulating complex stuff like chemistry. Still a tough nut to crack, even for quantum.
It remains a grand challenge. Quantum computers offer a path, but getting accurate, efficient simulations, especially with error correction factored in. Still a lot of research needed there.
And finally, this global quantum race, it feels intense.
It really is. The US, China, Europe, UK, Australia, Japan. Lots of investment, lots of competition. Navigating the geopolitics while still encouraging collaboration for the science itself, that's going to be crucial.
So for everyone listening, we've really gone from the weirdness of qubits and entanglement through the power of quantum algorithms and computers, the security of quantum communication, right up to the latest experiments. It's clear this isn't just theory anymore.
Not at all. It's happening now. The potential is immense, harnessing these unique quantum properties.
Yeah.
But yeah, the challenge of scale, errors, practical implementation, they're still very real. The progress is staggering, though.
And maybe, as we watch this global race unfold, the biggest question isn't just who gets there first, but how we, collectively, make sure this incredibly powerful technology actually benefits everyone. Something to keep thinking about, right? Thanks for diving deep with us today.